So thank you very much, Maria. And it's a great pleasure to have them. And I want to begin by actually thanking Samuel for looking after you guys so well. Thanks, Samuel.
Okay. Hi, everyone. I'm Maria. Thank you all very much for coming to listen to our talk. So the topic today is numerical methods for simulating spin chain dynamics. So we're just going to be going through everything we've been working on for the last 2 months while we've been interns here. For simplicity, even though we've been working on everything together, we're going to split up the topics into 3 main chunks. So I will begin by talking about the Monte Carlo simulations that we worked on with Samuel, and then Curtis will speak a bit on machine learning for quantum control that we worked on with Luke, and then Maxime and Cillian will talk about the project we worked on with Shane on fermionic representation of spin chains. Okay, so the Monte Carlo method. What is it? It's a method of obtaining a sequence of random samples from a probability distribution. Why is that so important? Well, it's a way of importance sampling. So say you have a probability distribution of interest, but for some reason or another, it's impossible or simply very difficult to directly sample. You can use the Monte Carlo method to get samples from a probability distribution that is identical to the one of interest. So it allows us to solve problems where it's necessary to average over a large number of different configurations, where each of these configurations have the probability here, where xi are the samples, z here is the partition function, and s is the action, determining how energy costly each configuration is. So this method is universal and also quite simple conceptually, and so can be applied to a large range of areas, including used for numerical integration, optimization, and spin chain analysis. We worked on 3 different levels of complexity to this method. The first being to randomly generate points, where you randomly generate the samples and then weight them according to the computations you want to carry out and carry on that way. Or secondly, to produce a Markov chain, which is basically a list of the random samples, but each has the same probability distribution as the one of interest. Or thirdly, to use Hamiltonian mechanics as a way to produce this Markov chain. I'm going to focus on the second and third of these in this talk. So the Markov chain, there are a number of different ways you can produce this. We use the Metropolis-Hastings algorithm, and is carried out as follows. So you begin by randomly generating the first value, or if it's not the first loop, you use the last configuration that was generated, and then you generate a new random value. And then you use the Metropolis test to test if this move is accepted or not. The test here is, it's the exponential of the change in the action between this new value and the previous one. If this is less than or equal to a randomly generated number t between 0 and 1, it is accepted and it becomes the new initial value. If not, it's rejected and then replaced with the previous value, and this process is repeated. So what you're left with then is this Markov chain, and you can use these values in computations and to make estimates on properties on the probability distribution as if these values had been directly sampled from the one of interest. And yeah, they'll have the same distribution as the one that you wanted to look at. Okay, so then furthering this process, we also looked at the hybrid Monte Carlo, which works in a similar way. It uses the Metropolis algorithm, But in this case, there's also the addition of a Gaussianly distributed momentum vector. This momentum is independent and random and doesn't contribute to the end result, and the momentum values are discarded after the test has been complete. So why would we do this? Well, the main reason is that it allows for larger steps, removing the limitations on the correlation length of the steps in this model, which means that each value is more likely to be dissimilar from the last, and leads to a quicker convergence rate to the distribution that you want, and avoids the slow exploration of the space that's characteristic of previous models. So it works as follows. Instead of just initially generating an x value, you also generate randomly a momentum value. And then you evolve these values using a numerical integrator. The one we used was the leapfrog method, and it works like this. So you take your initial momentum value and you evolve it 1/2 step. In this equation here, epsilon is the step size and U is the potential energy. So you evolve the momentum 1/2 step in time, using this equation here, where this is the initial momentum value, and then this is the initial x value. And then you take the initial x value and you evolve it 1 step in time, using this equation here. But now the momentum value you use is the one that you generated previously from this equation here. And then you generate, you evolve the momentum 1 step in time, where here this value is the one that you calculated in this equation, and this value here is the one you calculated in this equation. So it might be a bit more clear looking at this diagram here. You take the momentum, initial momentum value, and you evolve it 1/2 step, and then you take the position, and using that generated momentum value, you evolve this 1 step forward, and then using this value for the position, you evolve the momentum 1 step forward, and then so on and so forth until it's complete. And then you carry it in the exact same way as with the previous model. However, instead of just using the action in the metropolis test, you now use the Hamiltonian. So it's the difference in Hamiltonians between the two values. But otherwise, it's the exact same. Okay, so an application that we studied using this method was the Eisen model. It's a way to study the behavior of ferromagnets, and allows us to solve problems without taking the more complex aspects of the system into account. So the model is set up as follows. You take a lattice of dimensions L by L, and then you place spins of 1/2 at regular points on the lattice. So there's 2 spin states up or down. And then these spins are limited to nearest neighbor interactions. So what that means is that they can only interact with the other spins that are below them, above them, and to the left and right of them. And then we enforce periodic boundary conditions on the lattice. The energy at a particular site I is determined by this equation here, where J is the coupling constant, SI is the spin at site I, and it's summed over IJ, where J are the nearest neighbors to I. So this can be seen more clearly here. So this is the lattice that you generate, where at regular points there are either spin up or spin down on the lattice. And then if this is site I, its nearest neighbors J are, so there's 4 of them, the above, below, right, and left. And then to understand the periodic boundary conditions, it's quite easily understood if you visualize a torus with the spins located on the surface. So then you can see that the spins on the rightmost like edge of the lattice will interact with the spins on their geometric opposite on the left. Okay, so this is important because the energy of the system is dependent on spin alignment. So spins that agree on alignment usually have a lower energy than those that don't. And so this model can be used to identify a phase transition as it's dependent on temperature. And then why would we use the Monte Carlo method here? Well, for large n, so where n is the number of spins in the lattice, computations become way more time consuming. So this is an ideal method because since there's two spin orientations there, and then n number of spins, there are 2 to the power of n different possible states for the system to be in. So the algorithm that we used, this image here shows a flowchart of the logic behind the algorithm that we used. So you initialize this random lattice, the one that we saw in the previous slide, and then you choose a random site, and you determine whether if changing the sign of the spin, so since it's only up and down, it's just -1 or +1, if changing the sign would result in the energy of the system becoming lower, so whether the change in energy is less than or equal to 0. And then if this is the case, you change the sign and then record this energy change. But then if that's not the case, we use the metropolis test again to decide whether or not to flip the sign. So if the requirement is met, we change it. If not, we discard it and repeat it again at a different random location. And then this is repeated several times over the whole lattice. And what you're left with then is a Markov chain of these energy changes. And then you can perform calculations on these. We calculated the expectation value of this energy. And then we repeated this for a wide range of temperatures in order to determine the phase, what temperature the phase transition occurs at. So these were the results that we got. This figure A on the left here was taken from the paper that we were reproducing the results from. So here you can see it's set for 4 different dimensions of the lattice, going from 2 by 2 to 16 by 16, with the curve being more pronounced as the n is increased. And a phase transition occurring at approximately 2.1, 2.2. So our results nearly mirror this. Our L equals 2 is not as smooth, but that could just be due to the number of steps we took, since it's the energy per spin. Obviously, the more samples you make, the smoother this curve would be. But as you can see, our L equals 20. Our curve mirrors nearly exactly the expected result, with a critical temperature occurring at roughly the same place. And then furthering on from this, the Ising model has its limitations as it only allows 2 spin states, the up and the down, but this can be generalized to an arbitrary number of spin states in the Potts model, where the only difference is that the energy is defined by the Kronecker delta of the 2 spin states I, J. So if I and J, the sites I and J have the same spin, it will equal 1. If not, it will equal 0. So then we carry this out for a lattice of dimensions 10 by 10 for 10 spin states. And these were the results we got. So the energy per spin versus the temperature, and you can see there's a clear transition at the temperature T equals 0.72. This compared very well to the paper we were comparing our results to when reproducing the work of, that they got their critical temperature at approximately 0.7. And then this is the heat capacity versus the temperature. So there's a spike at this critical temperature. And then This graph here shows the time dependence of the internal energy on this lattice. So you can see there's fluctuations of the first order transition in the 10 states POTS model. So this further confirms our claim that a first order transition occurs at this site, at this temperature. Okay, so that's everything I have to talk about today. Thank you all for listening. I'll now hand it over to Curtis, who's going to speak a little bit about machine learning for quantum control.
Great, thanks very much, Maria. So I'll just get my screen sharing. Okay. Okay, so today I'm going to speak about the work that we did with Luke, looking at machine learning and its use for quantum control. So I thought for just to start the talk, I would imagine everyone here has heard of machine learning, but it's probably worthwhile spending a little bit of time demystifying it and talk about what I actually mean when I say it in the context of using it in the physical sciences. So at a very basic level, when I say machine learning, I just mean a system that has the ability to improve itself and make decisions without explicit programming. And then whenever we talk about machine learning, it tends to be broadly divided into 3 different subcategories. So I have a few little little cartoons describing this. So for supervised learning, which is probably what would be most widely recognized by people when they think of machine learning, we have some data. This is images of animals, and they have a label of whether they're a duck or not a duck. And this is fed into the algorithm, and it performs its own optimization of building a relationship of what it means for an image to contain the duck or not, be it a beak or webbed feet. And then we can feed it new information that it then makes a new prediction without a label. So we won't be focusing on this too much today in this talk, but I thought it would be worthwhile just stating it as well. Unsupervised learning then is similar, but it's the algorithm is not fed any labels to begin with. So usually it will perform some form of clustering and identifying features that are similar among the data points that it's fed. And there's other forms of unsupervised learning. Anything that is data without a label distinguishing it is classified as unsupervised, but clustering would be one of the most common ones. And then the third and final is reinforcement learning, which would be a more specific technique. It's been seen recently in the documentary AlphaGo, which is a documentary made by the company DeepMind, who's a subsidiary of Google, and recently they produced a reinforcement learning algorithm that was capable of solving, capable of playing the game Go, which is a Chinese board game with a huge number of moves that many people assumed that a machine was never going to be able to play. And it actually beat the world champion. And here you can see the world champion playing against a human who's obeying the instructions of the AlphaGo algorithm, and it's telling him what to do and what moves to make. So the reinforcement learning works off of having an agent, is the terminology, with a strategy, and it carries out that strategy, and then we have a reward function that's coded in that tells the agent how well that strategy performs, and then it makes a new decision on what strategy to perform on the next iteration. So these have uses in the physical sciences. Over the last couple of years, there's been an explosive growth in how much machine learning has been used in the physical sciences. Some areas that would come to mind would be astrophysics has a lot of use, and it would get use out of supervised learning, having images of galaxies or clusters that maybe it's previous data that has been labeled, and then it can train on it and then make predictions on new images would be a good example. But I think it would be fair to say that unsupervised and reinforcement learning are being used more in the physical sciences now, especially in the context that I'm going to talk about of quantum information science and quantum control, because it has the ability to tell us new information about a state that we necessarily don't actually know anything about yet. So Specifically, I'm going to be talking about quantum control. So this is this concept that if we have, like an initial state vector, and we have a target state vector that we want to go to on this illustration of the block sphere, which was kindly provided by Luke, and we have a Hamiltonian, and we're allowed to change some parameters of the Hamiltonian. Say the magnetic field would be a common choice. We give this information to the algorithm. We say, okay, this is where we start, this is where we want to go, change whatever you want, and it varies the magnetic field in such a way to get us to the target state. Now, to do this, we have to have some way to evaluate how the algorithm is performing, and this is a very it's a very keystone thing in a part of machine learning, in that all of machine learning algorithms have something called a cost function, or in reinforcement learning, it would be a reward function that analyzes the effectiveness of the behavior of the algorithm. So this is normally a mathematical function that varies between 0 and 1. And quantum mechanics naturally provides things that can be used as cost functions quite easily. So in this diagram, it could be the probability amplitude of after time capital T has evolved and the state's been allowed to evolve through the path that the algorithm has determined. Where does it end up? How close is it? And the probability amplitude is a very good measure of that. And then if it's a perfect optimization that the algorithm has produced, then it lands exactly on it, and it has a cost function of 1. So this has been done before using reinforcement learning, which I think you can imagine why that would be useful, because the algorithm has a strategy of how to generate a magnetic field to get across the block sphere. But reinforcement learning is quite difficult to implement. And whenever we started working with Luke, he was speaking to us about this idea that he had about using unsupervised learning and using gradient descent instead as a simpler method of implementation. So that's what we were looking at and seeing if we could get the same results. So we had a Hamiltonian that looks like this, and the variable here is actually the magnetic field with time. And we begin with the ground state with the magnetic field at -2, and we begin with the ground state of the Hamiltonian in that case. And our target state that we want to go to on the other side of the block sphere that you saw in the diagram is the ground state when h of t equals 2, where this is the capital T at the end of the evolution time. So we use the fidelity as our cost function of measuring the effectiveness of the algorithm. And then we implement gradient descent to generate this profile for h of t, because we split it into a discretized time lattice of array values. And for each one, we treat it as something that the fidelity is dependent on and something that we can optimize over. So we perform this gradient descent where each element of the array is iterated upon, and we move towards the gradient. It would technically be called gradient ascent because you're moving in the direction of the gradient. Normally this would be a negative, but here we have the gradient of the fidelity with respect to this element of the magnetic field array. And obviously if this is positive, then that means that we move in the direction of the increasing gradient. So we move towards the local maximum and optimize the fidelity so that the final state is close to the target state. And if it's negative, then that means that we move away from the local minimum and still we move towards the local maximum. And this LR stands for learning rate, which is another one of these things similar to the cost function where there's quite a lot of nuance to it, and there's no way I can do any justice to it. But it's essentially, for our purposes, something that determines the sensitivity of how quickly the algorithm will converge towards the local minimum. So we carried this out, and these were the results that we saw. So we did it for 2 different total time evolutions of total time that we allowed the state to evolve for. This is 0.5 for the total time. And we see here we start at a fidelity of about 0.38, and it plateaus after 1,000 iterations towards about 0.5. So even after 1,000 iterations of the gradient descent, the algorithm's not able to find a magnetic field profile that can actually bring it particularly close to the target state. And this is the magnetic field profile that we see it generate. It starts at 2, jumps down to -2 in quite a sort of discontinuous way. But then if we allow it extra time and we give it a total time evolution of 3 instead, we see that immediately, even before the gradient descent has really been implemented, it starts at a much higher fidelity because there's more time. And we begin with a magnetic field that's randomized and then allow the algorithm to optimize over it. With more time, it's somewhat easier for the state to naturally move to where we want it to go to. And then after around 400 iterations of the gradient descent, we're actually able to achieve a fidelity of 1, meaning that we can control the state exactly to the target that we want it to go to. And we see that we get a profile that looks something like this. It's much smoother, much more continuous for the magnetic field. And we attribute that to, since the algorithm has more time to move the state, it doesn't need to behave in such a rash way. It can, take its time a little bit more. So we wanted to look at this relationship in a bit more depth between the total time allowed and the maximum fidelity that was achievable for the target state. So we saw this relationship, and once there's a fairly linear dependence for the majority of this, and then once we get to about 1, it starts to plateau for the total time allowed, and once we get to about 1.4, we're able to achieve that maximum fidelity of 1, and then any extra evolution time beyond that is just extra. So these are all promising results, and it's impressive that we were able to control this qubit in this way using a much simpler algorithm than what had been done before. But in order to produce results that are useful in today's landscape, we wanted to strive to be able to simulate more qubits. So as I'm sure everyone in the audience is well aware, the exponential nature of the Hilbert space means that on a classical computer, the ones we have at home, we can probably only model 10 qubits, maybe 20 at a push. But IBM's newest quantum computer has 53 qubits in it, and Google has recently released a prototype that has 40 or 54 qubits in it. So we would want to aim for a framework that can simulate more qubits than that. And that is what Cillian is going to talk about next. So I'm going to hand off to him.
Thanks, Curtis. Hey, everyone. Thanks for coming. I'm just going to share my screen. Can you all see that? Yeah? Okay, great. So for the rest of the talk, we're going to talk about the decoherence of quantum systems, which is what we're working on with Shane. Now, the decoherence of a system due to interactions with an environment is an unavoidable part of quantum computing, so it's important and very useful for us to be able to model it. One way we can model it is by using a so-called brute force approach, where we model the system and the environment in its entirety. But this is very computationally expensive, because even if we have a small system of interest, if the environment's large, then this is going to take a lot of time to model the whole thing. Similarly, common approximation methods only have limited domains of validity, and in particular often can't model strong coupling. So for this project, what we focused on was a situation where we can simplify the problem without losing any accuracy, and that's for a quantum XY spin chain. In particular, we're going to model the decoherence of a single spin half particle, which is our system S, and it's at the end of a spin chain, and the rest of the spin chain here, E, is going to function as the environment. And how we're going to do this is we can map that spin chain to a free fermion model via a Jordan-Wigner transformation. Then we use the Gaussian nature of the resulting system to speed up computation time. This has been done, or a similar thing has been done by Rossini et al. They considered a transverse magnetic field acting on the first spin. What we do beyond that is we include an arbitrary magnetic field for the first spin. So we can also have X and Y components of the magnetic field here. We'll see later that this seems like it destroys the Gaussian nature of the problem, but this can be restored due to a trick from a paper by Culpa, and I'll explain all this more later. The result of this is that we end up being able to work with matrices of size of order n compared to matrices of size of order 2 to the n if we just use a straight brute force approach. So this is obviously a very big exponential speed up, and in particular with the brute force approach we were only able to get up to spin chains of length about n equals 20 or even less, whereas with the new approach we can model spin chains of size up to 300 without too much difficulty. And this is important because certain phenomena do only appear with these larger spin chains. So for the next few minutes, I'm going to talk about how we map this spin chain to first a fermionic system and then a Gaussian system. And then Maxime will talk about the results we got using this setup. So first, I'll describe our model. Again, our system S is a single spin half particle in a magnetic field. The magnetic field is given by omega here. So the Hamiltonian of the system is just here. And where this sigma 1 vector is a vector of the x, y, and z Pauli operators acting on the first spin. Then we have our environment Hamiltonian here. So that's the other n-1 spins in the chain. And we have the Pauli z operator acting on them, representing a transverse magnetic field on each of them. And then we also have these nearest neighbor couplings here. Again, and now we've written these in terms of sigma minus and sigma plus operators. It's probably more conventional to use sigma x and sigma y operators here. That's where the xy spin model gets its name, from these xx, xy, and so on interactions here. But we've used minus and plus operators because they just behave nicer after the transformations we make. Then finally, we have the interaction between the system and the environment, which is given by this V Hamiltonian here. So we have these again, the sigma minus, sigma plus coupled to the sigma 2 plus, which is the Pauli operator acting on the second spin in the chain. And again, these represent xx, xy, and so on interactions. And then we also have this zx and zy interaction here from the z operator, or the sigma z operator. Now we're somewhat limited in which couplings we can choose here and which terms we can include in the Hamiltonian overall, because we do need everything to work out after the Jordan-Wigner transformation, so we can get back to a Gaussian type system. So we're somewhat limited here, but we still have a very large amount of things we can do with this Hamiltonian. It's still quite general. So the next thing is our initial state, which is going to be a tensor product of a state of the system, which is the first spin, and then a state of the environment. So we take the initial state of the system to just be an arbitrary mixed state written in this form, where n is its block vector, as Curtis mentioned before. And again, we have just these Pauli operators here. And then the environment is just taken to be in a thermal state with inverse temperature beta. And then the z here is just a partition function given by the trace of this exponential here. Are there any questions about the model or the setup or anything? Okay, Grant, just stop me if there are any questions. So what we're going to try to do now is represent this spin chain as a fermionic Gaussian system. So first of all, I'll describe briefly what that type of system is. So suppose we have n fermions with creation and annihilation operators, an dagger and an, satisfying these commutation relations. So the anti-commutator of an and am is always 0. But if you have the anti-commutator of a creation and annihilation operator, that's 0 if they're acting on different fermions, but the identity if they're acting on the same fermion, given by this delta term here. So for notation, we introduce this vector alpha. I've written down alpha dagger here because it's easier to present. So alpha dagger has as its first n entries the creation operators, and then the last n are the annihilation operators. Alpha will be a column vector, and you'll have the annihilation vectors first, and then the creation vectors because the order is switched. So then the next thing we look at is these type of quadratic Hamiltonians that are quadratic in the fermionic operators, as you can see here. And we write these as a matrix equation here. So the half is just for convention, and alpha dagger H alpha, where H is a 2n by 2n matrix. Now it turns out H can always be chosen to be of the form shown here, where mu is Hermitian and nu is antisymmetric. And you can just find that from the commutation relations. So the next thing we do with these Gaussian systems is, given a state rho, we define its covariance matrix lambda. And the entries of lambda are given by these expectation values of the commutators of fermionic operators here. And then notice this is an alpha, not an A. So these can each be either creation or annihilation operators. And again, lambda will be a 2n by 2n matrix. And the great thing about lambda is that it satisfies this very nice Schrodinger type equation here of d lambda dt is equal to minus I times the commutator of H and lambda. And this is where the big speed up happens, because lambda is only 2n by 2n, whereas the state rho is 2 to the power of n by 2 to the power of n when you write it in matrix form. So it's far easier to evolve lambda than rho. And we'll see later that we can get back a lot of information about rho just from lambda. But as you can see here, the definition of lambda is it's kind of not completely straightforward to compute this, but in certain circumstances it is. So if we have a special type of state called a Gaussian state here, which is a state that can be written in the form rho is equal to this normalization factor times this exponential here, where inside this exponential we again have this quadratic sum of, the sum of quadratic fermionic operators, which again we write in this matrix form. And like the Hamiltonian, this matrix A, which is again 2n by 2n, can be chosen to be of that same form with mu Hermitian and mu antisymmetric. And then the great thing about this is that these types of states are characterized completely by their covariance matrices via this relation here of lambda is equal to minus the hyperbolic tan of A over 2. So now what we can do is, given an initial Gaussian state, we write it in this form here, find the matrix A, find lambda from A, and then we can evolve lambda by this equation here, which again is much more efficient than just evolving rho straight away. And then we can find out things about rho. And again, I'll talk about that later on. So now what we have to do is we have to map our original spin chain to this, first a fermionic system and then a Gaussian system. So what we do first is we use a Jordan-Wigner transformation here. So we define these operators AN as a product of sigma z spin operators and then a sigma plus acting on the nth spin. So these become our new creation and annihilation operators, and they can be checked that they do satisfy the commutation relations we want. And then in this new basis, the Hamiltonian can be written like this. So I'll just go through some of these terms. So like this term here was a sigma 1z, and now sigma 1z has become this commutator of A1 and A1 dagger, which is quadratic. Similarly, all these sigma nz's transform the same way. And then these xy and yx, etc. couplings also become these quadratic terms of the fermionic operators that are acting on adjacent spins and multiplied together. But you'll notice that our Hamiltonian isn't fully quadratic. For example, we have these linear terms here, and both of these come from the x and y components of the magnetic field, so they do introduce linear terms. And similarly, one of our coupling terms here also becomes linear. So we're not going to be able to use the Gaussian formalism straight away. Similarly, our initial state rho becomes can be written in this form, which is its the derivation of this presented in the paper. It's not obvious. But again, it's not quite Gaussian because we have these linear terms here. And it's worth pointing out that this only works if the initial state of the system, that is of the first spin, isn't pure or fully mixed. So you need the magnitude of the block vector to be strictly between 0 and 1. If the magnitude is 1, then that means you have a pure state. And if it's 0, it just means it's fully mixed. And it causes issues here with this, because this constant here isn't defined if n is either, if the magnitude is either 0 or 1. But it turns out this actually doesn't really present a problem because we can just deal with it in a limit. And now it's not quite we're not taking a limit of this, it's more that what we do exactly, and this is described more thoroughly in the paper, is that we can find lambda using this method for like sort of mixed states approaching a pure state. And then lambda is continuous in rho. So, and lambda is well defined for pure states. They don't have to, it doesn't have to be a Gaussian state for lambda to be defined. So we can just find lambda for pure states without too much difficulty. And again, that's described in a lot more detail in the paper, but I don't really want to focus on it here because our main problem is that we have these linear terms. Are there any questions about any of this? Right, grand. So how we resolve the problem with the linear terms is we use a method due to Culpa, where we introduced a ghost fermion, is what he calls it, at site n+1 in the chain that isn't coupled to the chain. And then we define this unitary transformation U, given by this sum of quadratic and then linear terms in the creation and annihilation operators corresponding to this new fermion. And the exact form of this isn't too important, but what's important is how the fermion terms transform under this operator. So for example, an, a linear term will get mapped to an times this difference of the operators corresponding to the new particle. And furthermore, the quadratic terms are left unchanged. So if we map our whole system under this unitary transformation into this new system with n+1 fermions, if we just go back, you see these red terms will all become quadratic, all the linear terms. So we'll have a quadratic Hamiltonian, and we'll have a Gaussian state, again, as long as this isn't pure. And so now we're in a position to use all the tricks I described earlier with the Gaussian systems. So what we need to do then is to recover the state of the system, which is the first spin, from the matrix lambda. And it turns out this is quite easily done because we notice that the state of our system S is fully characterized by the expectation values of sigma 1z and sigma 1 plus, which are given in terms of the fermionic operators as these equations here. And then we also have the basis transformation to take into account. So sigma 1 plus is then given by A1 times the new fermionic operators, whereas sigma 1z stays unchanged, and it's just this commutator here. And now lambda is defined just in terms of expectation values of these commutators. So all we have to do to find the expectation values we want is to just find the relevant terms in lambda. And sure enough, this isn't too bad. We find that the expectation value of sigma 1 plus is just half, and then the difference between two entries in lambda. And there's a few choices for this because there's certain symmetries in lambda. And then similarly, the expectation value of sigma 1z is just a single term in lambda. So it's quite easy to extract the state of the first spin from lambda. So then just to summarize everything we've done here is we've started out with a spin chain. We map it to a system of fermions using a Jordan-Wigner transformation, and then introduce the ghost particle to make it into a Gaussian system. So now what we do, if we want to model a particular situation, so we fix the constants, lambda, n, plus, minus, and omega, etc., the magnetic fields. And then we determine the matrix H corresponding to the Hamiltonian, which is now 2n+1 times 2n+1, where the plus 1 comes from the ghost particle we've introduced. And we determine as well the initial covariance matrix, lambda at time 0. And then we determine it again from the matrix A via the hyperbolic tan relation, or as a limit in the case of pure states, which is what we did most of the time. We were looking at cases where our initial state was pure. And then once we have these, we just evolve lambda by this Schrodinger type equation. And then at any time t, we can find the state of S just from lambda of t. And then the big advantage, just to reiterate, is that lambda is just a 2n plus 1 by 2n plus 1 matrix, whereas rho is 2 to the n by 2 to the n. So it's far, far easier to evolve this equation here than to evolve rho straight away. So Maxime will tell you now about all the results we managed to get from this, if there's no questions first.
I think we're going to take questions afterwards, so that's fine.
Oh, Grant. Yeah, thanks.
Okay, thank you, Cillian. So I'm going to share my screen. Okay, you can all see this. Okay, so we studied the decoherence of the system. So to do this, we first need to define some measures. Actually, I'm going to put this in full screen. So we need to define some measures of the decoherence. There are different measures that exist in the literature. One of them is purity, which, as you probably all know, is a trace of the density matrix squared. So the purity goes from 0.5, which is a purely decoherent, well, I shouldn't say purely, it's a fully decoherent state, to 1, which is a pure state, so a coherent state. In our case, we studied systems in the form given here, so half of the identity plus nx sigma 1x plus n1 sigma 1y plus nz sigma 1z. And in this case, it's quite straightforward to show that the purity can be given by this equality here, so half of 1 plus the magnitude of the block vector. So this is the purity is the main measure we're going to use, except in one particular case, and you'll understand why later, where we'll use the Loschmidt echo, L, which goes from 0 to 1. So 0 is again fully decoherent, and 1 is a fully coherent state. And in the case we're going to use this measure for, the pure state, the initial state is going to be pure, and the environment is going to be in the ground state, which means beta, the universe temperature, is infinite. So in our case, we used 1000, and you'll see that this doesn't really pose any problems later on. And in this case, the Loschmidt echo, which is the decoherence of the absolute value squared of the decoherence factor, can be simplified as the absolute value squared of the ratio of the off-diagonal element of the system's density matrix times t over the value at t equals 0. And an important thing to note is that when both of these equations are valid, then for any two positive times t1 and t2, there exists a strictly increasing function that relates L to P. So if L of T1 is greater than L of T2, then P of T1 is greater than P of T2. Okay, so now I'm going to present the case where we use the Loschmidt echo. So we use this measure because we compare our results to a paper by Rossini et al., who also used the Loschmidt echo. It's just easier to compare our results. So we selected the parameters in our model to match as closely as possible to what Rossini and et al. Did. There remain two very important differences. So firstly, they have a different coupling between the system and the environment. So they coupled using sigma 2z, and we use sigma 2 plus and minus. So in other words, sigma 2x and sigma 2y. And furthermore, they used closed boundary conditions while we used open boundary conditions. Nevertheless, we see quite similar results in the behavior of decoherence. So we see So lambda here is our omega nz, where n is not equal to 1. So for when lambda is less than 1, they have oscillatory behavior, which is also shown here. But when lambda is greater than 1, then this behavior tends to flatten out. So it's kind of like an underdamped oscillator. And there is, as you can see, a critical value here at lambda equals 1, which is also present here, where the decoherence goes to a minimum. And well, it only comes back up due to finite size effects. But in our case, it just continues at a minimum. You can also, as I mentioned, see the finite size effects here. But I'll go back to this later on. Okay, so this is a plot of the minimum Loss-Schmidt echo, so this measure here, and the long time Loss-Schmidt echo. So when we had oscillations, we took the average of the minimum and the maximum in the later times. And as you can see, at the critical point, so 1, we get a very sharp increase in both the minimum and the long time echo, which are long time Loss-Schmidt echo, which is the same results as Rossian et al. It's what characterizes this critical point. So note that this would also be seen if we had used the purity, because as I mentioned, there's a strictly increasing function relating L and P. So when we had done this, we changed the parameters a bit to see what would happen. We found that the critical point, so the location of the critical point is independent of omega 1z and lambda 1z. So if you look at the purity here, this is for lambda 1z equals 0.25i, so it's an imaginary number. And we can see, if it's kind of hard to see here, but the long time purity is about the same up until 1, and then as soon as omega nz increases beyond 1, then this starts to rise. So we would have a similar plot here, except for the minimum. The minimum is more continuous here, but we still have this critical point characterized by the long time Loss-Schmidt echo. Here on the bottom right, we have let me check my notes. We have lambda n plus equals -1 and lambda n minus equals -4. And we can again see similar curves as this plot. However, the critical curve here is actually at 4. So we conclude from this that the critical point scales with the maximum of the absolute value of these coupling constants. And we also checked at omega nz equals 1, and we see nothing particularly interesting. It's just oscillations similar to what we have at 3.9. So this suggests that there's only one critical point at omega nz equals 4. Note, however, that these conclusions are based on relatively few runs, so take everything with a grain of salt. But yeah, so that's our best guesses for now. You can probably also see these sort of strange oscillations here, which are ramping up in magnitude. These are finite size effects again, which I will come back to later. So all of the examples I just showed you were where the system Hamiltonian commutes with the total Hamiltonian. So we also did some tests with when the Hamiltonians did not commute. And well, we get some pretty messy behavior, and it's quite difficult to know really what's going on. If you look here, you might suspect there to be some sort of critical point, maybe between 0.5 and 0.9, but I've checked and I couldn't find anything. So it might be some sort of continuous transition, but it's not very clear. Here on the right is probably the cleanest decoherence behavior we have, where the Hamiltonians don't commute. It's very similar to what we have here, but it's more elongated, as you can see, and also the curves are, there's just a lot of rapid oscillations along the curves. Unfortunately, we haven't had much time to delve into the reasons why this behavior occurs, but it would definitely be an interesting problem to look at. Okay, so now we move on to temperature dependence. So interestingly, we found that the purity and also the ultimate echo is temperature independent when the system Hamiltonian commutes with the environment and interaction Hamiltonians. This could be an if and only if relation, but it's quite hard to check by just running a few tests, so we don't know really. So we see on the bottom here, the bottom two figures are for our decoherence behaves at the critical point, I believe, where the Hamiltonians do not commute, or do commute, sorry. And you can see that there is no temperature dependence since the black, red, and green curves are just under the blue curve here. But in these two situations, we have temperature dependence because the Hamiltonians do not commute. Now you might not see the green curve here because it's on the blue one. I think there might be like a pixel of green in this curve, but anyway. So this relation between temperature dependence and commutation of the Hamiltonians is a characteristic of our spin chain, so it's not true in general. So if we look at this example given by Shane, this commutes, but if we do the maths, then it actually is temperature dependent. So we don't know why we have this relation between temperature dependence and commutation. It would be an interesting problem for sure, but yeah. So it must have to do with the properties of the spin chain, but we don't know which yet. Also, important detail. So here we see that the decoherence is far lower for smaller beta, so for larger temperatures, which is exactly what we would expect from thermodynamical arguments. And furthermore, we can see that, as I mentioned, the green curve is pretty much hidden under the blue curve. So beta equals 10 and beta equals 1000 is basically no difference, which is why we can use beta equals 1000 to approximate the ground state of the environment. Okay, so finite size effects. So we saw finite size effects in a few graphs, as I mentioned. From our tests, we can, I think, safely conclude that the time at which finite size effects are first seen, so T star, is approximately given by n over the maximum of lambda n plus and lambda n minus, or their magnitudes. Now note that we only used, we didn't do individual adjustments of these, so for all n not equal to 1, these were the same value, and similar for this. So it might change if we adjust individually these items, but when they're adjusted in bulk, then this holds, as we can see here. So if you consider the lambda n plus equals 1, we see that, so the green and blue, the green and black curves, we see that they're on top of each other until finite size effects start happening at n equals 40 for the black one and n equals 80 for the green one. And then for lambda n plus equals 4, these are divided by 2. So this is our, this is the reason I think this is the correct formula. Now this holds for open boundary conditions. For closed boundary conditions, we think this is just divided by 2. But if I come back to here, we see finite size effects here at t equals 150, and lambda n plus and minus were 1, but their spin chain had a size of 300, so that wouldn't make sense. So what can we conclude from this? Well, maybe we can think of these complete constants as kind of the speeds of transmission of information. So when this is bigger, then the information travels faster, and so reaches the end of the chain faster, and then reflects back and starts interfering with the incoming information, causing these effects. And then for when we have closed boundary conditions, then the information can travel in 2 directions and meet halfway, which would explain the factor of 1/2 here. Okay, so this is most of what we've done. There's still a lot of things to do. So firstly, more exploration of the parameter space. So we haven't had much time to work on this. So it's quite likely that we missed some interesting phenomena. Also, so like critical points. Also, we can, as I mentioned, try as individual adjustments of each coupling constant instead of applying a single parameter for all n. Also, in all of the examples I've showed you, we used the system was initially pure. It would be interesting to also look at cases where the system is initially mixed. Furthermore, we should try to understand why this particular spin chain shows temperature-independent decoherence when the system Hamiltonian views the total Hamiltonian. And as we said, it's probably due to some of the properties of the spin chain, but we don't know which yet. Also, it might be interesting to study the relation between decoherence and entropy and entanglement. This, I think, has been done before, but with different spin chains. And finally, there are a number of applications that we can do. So one is quantum thermometry. So if you want to do quantum thermometry with this spin chain, then we're going to need to use a non-commuting Hamiltonian, as we saw here. But as I showed, these non-commuting Hamiltonians can lead to quite messy behavior. So it's possible that our best bet is to use the parameters which give this decoherence behavior, because it's actually quite neat and fairly easy to analyze in comparison. So quantum thermometry has been done before, but on different spin chains by, for example, S. Vazavian et al. Another application is remote parameter estimation, which has been done by Hugus et al. And another application that Kurt is going to talk about next is quantum control. So thank you for listening, and I'll pass it on to Curtis.
Okay, great. Thanks, Maxime. So I'm going to start sharing my screen again. Sorry if anyone has motion sickness passing you between all these screens. Okay. Is that okay? Everyone can see all right? Yeah. Okay. So after we had developed this framework, it seemed quite natural to try and come back and connect it with the work that we had done with machine learning, because as Maxime was saying, we were left with quite a few questions about the behavior of the spin chain. So we looked at seeing if we could use this quantum control framework that we had developed previously to try to maintain coherence of the system, which we took to be a measure of the purity, try to maintain the purity of the system, which we took to be a measure of the coherence. So in this case, we had used trace of rows squared of the system as a measure of the cost function for the gradient descent algorithm, very similar to what we had done before, but now it was the chain. And again, it was fed the magnetic fields as a feature to change and to try and optimize the cost function to 1 in order to keep the system as pure as possible throughout time. So all the coupling constants were set to 1 for this case to allow free transfer of information across the qubit sites. So when developing this, the thought came up of how you would actually implement this cost function, because with the previous example that I talked about, when we had 1 qubit and we knew the state that we wanted it to get to at the end, it's very natural to compare the fidelity of the state after its time evolution to the target state. But for this case, it's not so clear cut, because we want to incentivize the algorithm to try to maintain purity for as much time as possible, not just the end state. So initially a thought was to try to use an average of the trace of rho squared throughout all time points as our cost function. But then we realized that we did want to incentivize maintaining purity at a later time, because that would be more valuable than purity at the start, because we begin with an initial pure state. So we settled on using this weighted average for the cost function, where these are our weights, which allows for quite a lot of nuance. We just went for an array of values that go from 1 to 2. So the first trace of rho squared, the first measure of the purity in time, is half as valuable as the final measure of purity in time. Also, I didn't actually mention this, but with the previous implementation of machine learning, we had used differential programming, which is programs that are capable of calculating the gradient automatically and very quickly and efficiently. It was harder to implement for this case, so finite difference methods were used, but that naturally meant that the algorithms performed more slowly. So we ended up implementing stochastic gradient descent this time instead of regular gradient descent, which just meant that we only sampled 20% of the purity values in time at any one time for the algorithm to optimize. So actually looking at the results of these, we see some quite promising behavior. This is only for 100 iterations because, like I said, the algorithm was quite intensive. But you can see here this black line where you have the initial state vector that starts at 1 for a completely pure state, and then quickly in time drops down to 0.5, being maximally mixed. And then after iteration 20, we see some improvement of the algorithm maintaining purity for a longer period of time. But then once we go to iteration 50 and iteration 100, we see some really promising behavior here. It seems to actually be stabilizing the purity and managing to maintain it for a good period of time. So when we go back and actually look at the magnetic field that the algorithm seems to be suggesting, this graph is a bit hard to see just because the magnetic fields all overlap for time or for qubit sites that aren't the system site at site number 1. It appears that the algorithm opted to only change the magnetic field intensity at the first qubit to attempt to maintain purity, which is actually a very interesting behavior to see, because this is a conversation the 4 of us had previously had with Shane about this idea of if we were to increase the magnetic field in strength on the first qubit, it might develop the behavior of becoming dynamically decoupled with the rest of the system, which is what we believe we see is happening here, because the coherence is not being lost to the rest of the qubits. But this framework allows for quite a bit of exploration in some other areas. It would be possible to potentially fix the magnetic field on the first qubit and then see if the algorithm actually will change any of the magnetic field strength of the other qubits in the environment chain, to see if that has any effect on the coherence. And then additionally, this potentially would be useful in what Maxime was stating about if we wanted to use this spin chain for quantum thermometry, to explore the parameter space and see how we can maintain coherence and get a stable state for a higher temperature environment when the Hamiltonian doesn't commute with the environment Hamiltonian. So that's actually the end of the talk. Just before we take any questions, we just wanted to give a few acknowledgements to everyone who had helped us over these 2 months and given us their time. A lot of people in the audience today have spent some time to give us a talk about their research, and everyone's been very friendly. But in particular, we want to thank Luke Shane and Samuel for spending their time with us and actually getting us to the point where we can present these results and have this experience under our belt. And especially to Samuel and Denjo for actually coordinating the studentship and giving us this opportunity in general. But yeah, having said all that, I will leave the floor open to any questions if anyone has any.
Well, thanks to the four of you for fantastic presentations. They're incredibly well done, I must say. And let's take some questions.
So can I ask?
Please.
If you had 2 more weeks to work on something, what would that be? And don't worry, you don't have 2 more weeks, so.
Give our answer here, like, surprise, you actually can do it. I don't know about the others, but personally, I really would enjoy working more on the quantum XY chain stuff that we had done with Shane, because I felt like we were really starting to get somewhere where it was actually being promising, and I felt like we were doing like actual real science. And I think everyone sort of found something that interested them in a slightly different area there. So I think it would have been quite natural that the four of us all would have been able to do something slightly different and bring value to the problem.
You've said it all.
I have a question or two and just a few comments as well. Just first.
Yeah, please.
Yeah, so just really, really great presentations, and I was looking at the manuscript you wrote as well. It's like incredibly well done. I mean, not to say that our expectations were low, but I mean, this was a really, really, really high quality paper. You know, it's nice and feels like you're on the cusp of almost being able to produce something that, you know, you could write a paper on. Yeah, so well done to all of you guys, and of course also to Sam and Luke and Shane on all that. The question I had was with the last thing about the decoherence, which was I found very fascinating with especially with the machine learning. So you mentioned this. It seems that what you called it was a dynamical decoupling. Is that what you said? So that's it, somehow the ML algorithm has somehow found a way to somehow just adjust the magnetic field so that this spin chain remains pure. That's the general idea. And that is, was that with the things always anti-commuting or commuting, or I mean, was there?
That was with the commuting case, so it wasn't temperature dependent there.
Okay. No, it's very interesting that somehow it was even able to do that. I wouldn't have imagined that was even possible.
It was for very special values of the couplings, if I remember.
Okay. And then,
which may be a limitation there.
Yeah. Okay, but still pretty interesting that you can even get that to happen. Also, just on the extension of this Kalpa stuff. I mean, that was really well presented and seems like a very interesting trick. I guess, like, where do you? I mean, you guys have read the literature now. I mean, do you know? Have you found anything else where anybody else has used this trick with this ghost particle, or it seems to be relatively unknown?
Yeah, I think it hasn't been used too much in this context, like because it does definitely introduce more possibilities for using that Gaussian model to simulate the decoherence. Because like Rossini obviously was able to do certain things, also using the Jordan-Wigner transformation. But then the thing we do, it does limit our what couplings we can have. But as far as I'm aware, Rossini was limited as well, just in a different way. But yeah, I think there's definitely like just a lot we can do there.
Okay. Well, look, well done again, guys. Well done again.
Yeah, I would like to emphasize that those were very high quality talks, and I'm very impressed. Can I ask just, do you see a way of getting around the limitation of just dealing with Gaussians? Because Gaussians are rather special, and most systems in practice will not be Gaussian. Does somebody want to?
Well, I mean, the whole simplification does depend on it being Gaussian. So obviously we're losing something there. Like, I mean, even the fact that we can simplify it so much means that it's not a fully general system, obviously.
But can you imagine developing a perturbation theory around that? Possibility. It's too hard. You haven't thought about it. That's okay.
That's the basis of everything that is hard about what we do, then, Joe. Really, right?
Sure, I understand. But I imagine that one can probably perform perturbation theory around such a system that would give access to a wider class of systems. Do we have any more technical questions with regard to the presentations? Just maybe I can ask one more question. Do you see this machine learning as a possible alternative to the Monte Carlo and hybrid Monte Carlo that you began with?
Yeah, so that's actually something that I didn't talk about. Where when we were working with Luke, that we went and looked at simulating the same things with Monte Carlo and seeing what the results were. I think the two are definitely both valid, and the two can be swapped out for one another in many circumstances. But it just might be that some are a better fit for other problems than others. I think personally what I quite like about the approach of machine learning is the approach that I took at the very end, where it seems to have this ability to kind of tell you something about the system that you might not have known before. And it, depending on the problem, I think it can move more efficiently than Monte Carlo in some cases.
Okay, thank you. Any other comments or something? Anyone else want to join in? Maybe I'll stop the recording and we can leave it at